Acids and bases. We're going to use the Arrhenius definition. So an acid contains an excess of H+ ions. In other words, an acid consists of an H+ ion and some anion. Like for instance, HCl or H2SO4. Right? Acids are typically going to start with H. So the properties that acids have: a sour taste, although you probably shouldn't put stuff that you find in the lab in your mouth ever. You can also see the acid from this lemon over here is turning this blue litmus paper to pink. Acids have characteristic reactions where they will react with a metal and make hydrogen gas and a metal cation, and then they react with bases to yield water and a salt. They react with carbonates to give carbon dioxide. Let's look at some examples. Acid plus a metal. How about HCl plus magnesium solid? We're going to get H2 gas plus MgCl2. And if the acid is aqueous, then the magnesium chloride will be aqueous as well. And finally, to balance it, we need a 2 here. So, acid plus metal, hydrogen gas, and this is a salt. We'll come back to salts in a minute. Acid plus carbonate. Let's do HCl again, aqueous, and we'll react it with sodium carbonate, Na2CO3, aqueous. And for products, we are going to get H2O liquid plus CO2, and the CO2 formed as a gas, and we're also going to get NaCl, a salt again, and that NaCl is aqueous. And let's see, to balance it, I believe we need a 2 here, and we're good to go. Now, how about an acid plus a base? Well, first let's define what a base is. According to the Arrhenius definition, a basic solution supplies hydroxide ions. So, some common bases are metal hydroxide salts, like sodium hydroxide, or calcium hydroxide. These are bases. You put them in water and they dissociate into a metal cation and hydroxide anions. Ammonia is another example of a base. It has the chemical formula NH3. And it actually reacts with water to make a hydroxide ion. We can talk about that. Bases taste bitter. Like if you've ever taken Tylenol and you haven't swallowed it but chewed it, the horrible, horrible bitter taste is because Tylenol is basic. It turns litmus paper blue. It's got a slippery, soapy texture, and it neutralizes acids. Now to the Bronsted-Lowry definition. A Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Here are the Lewis structures showing the reaction that happens when you put hydrochloric acid, HCl, in water, H2O. The water actually acts as a base, and it steals the proton from the HCl. Right, so this arrow shows a bond forming. This arrow shows a bond breaking. And now, this hydrogen over here on the right-hand side is this hydrogen that came from the acid. Okay, so let's identify what was the acid and what was the base. The acid is the proton donor. So HCl is the acid. And the water is taking a proton from the acid, so it is the base. Let's go caps. Now, HCl and Cl- are related. The Cl- is what we call the conjugate base of HCl. And the H3O plus is what we call the conjugate acid of water. These conjugate acid-base pairs are related by a single proton. So, if you take a base and you add a proton to it, you get the conjugate acid. And if you take an acid and you subtract a proton from it, you get the conjugate base. Then there are some substances that are AmphipodIk. That means they're capable of acting as both an acid and a base. Water is an example. So for instance, I can take away a proton from water to give H plus and OH minus. That's water acting as an acid. And that means hydroxide is the conjugate base of water. Or, if I add a proton to water, that's water acting as a base. And I get H3O plus. H3O plus is also known as hydronium. And hydronium is the conjugate acid of water. Here's an exercise for you. Pause the video and work it out. So the conjugate acid of X is X plus a proton. In other words, HX plus. Now we have HPO4 2 minus. We add a proton to it, and we get H2PO4, and the charge is -2 plus 1, which equals -1, so H2PO4 minus. There are some compounds that don't contain any hydrogen ions, and yet they're capable of acting as acids. So, we need the Lewis definition of acids and bases for this. All compounds have electrons, so we define Lewis acids and bases in terms of electrons. So, think about what a Bronsted-Lowry acid is. An acid is a proton donor. So what does the acid do to things it encounters? Well, it gives them something that's positive. It makes their charge more positive. A Lewis acid is an electron acceptor. In the Bronsted-Lowry definition, a base is a proton acceptor. So it takes something positive from whatever it reacts with and makes it more negative. But if we're not doing proton transfer reactions, then to make something more negative, you just give it electrons. So the Lewis definition of a base is an electron donor. BCl3 is an example of a Lewis acid. Its Lewis structure looks like this. And if you look at the boron, it only has 6 electrons. So it really wants more, which makes it happy to accept electrons. NH3 is a Lewis base. Right, so there's the Lewis structure of NH3. And in the Lewis acid-base reaction of these two things, this pair of electrons on NH3 becomes a sigma bond to the boron. And the result of this is an adduct, where the boron has a negative formal charge now, and the nitrogen has a positive formal charge. So that's a Lewis acid-base reaction that is not a Bronsted-Lowry acid-base reaction. However, all Bronsted-Lowry acid-base reactions are also Lewis acid-base reactions. Therefore, Lewis is the most inclusive definition of acids and bases.